Now, recall that a rectifiable measure can have support equal to all of Euclidean space. So it doesn't have a tangent in the usual geometric sense, like with manifolds, but it still does have a tangent plane at almost every point in the sense of tangent measures. So given a M-rectifiable subset of Euclidean space, at almost every point inside the set E, there exists a plane, V sub z, so an M-dimensional plane, so that the tangent measures of Hausdorff measure restricted to the set E at the point Z are all just multiples of Hausdorff measure restricted to the same M-dimensional plane Vz. So what we'll actually show is something stronger, that if we take, so for almost every Z inside the set E, there's some constant Cz, so that if we take the continuous limit of r to the minus m times the blow-up tzr of Hausdorff measure restricted to the set E, so in other words, if we just continuously blow up Hausdorff measure on E at the point Z and let R goes to 0, this will converge to a multiple of Hausdorff measure restricted to this M-dimensional plane. So in effect, this M-dimensional plane Vz is the tangent plane of the rectifiable set. And this is what we mean by sort of a measure theoretic version of a tangent plane for rectifiable sets. So let's sketch some ideas of the proof. So recall that our goal is to show that at almost every point inside a rectifiable set E, the tangent measures are all just multiples of Hausdorff measure restricted to some fixed M-dimensional plane. Now, recall from our discussion about alternative definitions of rectifiability that E being rectifiable means that it can be covered up to set of measure 0 by bi-Lipschitz images of Rm. So what we're going to do is fix one of these bi-Lipschitz images and show that for almost every point in the intersection of E with this bi-Lipschitz image, that the tangent measures are all multiples of some fixed plane. So if we do this for one bi-Lipschitz image, it'll hold for all the other bi-Lipschitz images intersecting E, and thus prove the statement holds for almost every point inside E. Now, recall from our discussion about tangent measures that if you have a measure mu, and you look at its restriction to some set A, then for almost every point inside the set A, the tangent measures of mu and mu restricted to A coincide with each other. And in fact, if you take a blow-up of one measure with respect to some radii, it will equal the blow-up of the other measure with respect to the same radii and same constants. So what this tells us is that for almost every point Z inside the intersection of E with this bi-Lipschitz image, that if we take the blow-up of Hausdorff measure restricted to E, that's the same thing as the blow-up of E intersected with F, and that will be the same as the blow-up of Hausdorff measure restricted to the bi-Lipschitz image. So now this reduces the problem down to showing that for a single bi-Lipschitz function, showing that Hausdorff measure restricted to its image has blow-ups almost everywhere equal to some to Hausdorff measure restricted to a fixed plane. Now, because F is bi-Lipschitz, this implies that if we look at the push forward of Hausdorff measure on Rm under F, so we denote this measure nu, then because bi-Lipschitz maps preserve null sets, that implies that nu is mutually absolutely continuous with respect to surface measure on the image of F. So thus, again recalling the techniques from tangent measures, that if we have one measure that is absolutely continuous with respect to another, then the blow-ups of the measures are multiples of each other almost everywhere. So in particular, if we take the blow-up of Hausdorff measure restricted to F, this is going to equal a multiple of the same blow-up of the nu measure, where this multiple, so if nu is absolutely continuous with respect to Hausdorff measure restricted to Rm, that implies that we can write, or actually the other way around, that implies that we can write Hausdorff measure restricted to the image of F as equaling some density function g times the measure nu. And so this value A is just g evaluated at the point Z where we're blowing up. So thus, now it just suffices to show that if we take blow-ups of the push forward of Hausdorff measure under F, that they exist and are equal to multiples of Hausdorff measure restricted to a fixed plane for almost every Z in the image of f. So recall that our objective now is we have a bi-Lipschitz function f, and we want to show that for almost every z in its image, if we take the blowups at z of nu, these are equal to some multiple of Hausdorff measure restricted to an m-dimensional plane, where nu is equal to the push forward of Hausdorff measure on Rm under the bi-Lipschitz map f. So what I'd first like to do is just give a picture of what's going on before I launch into some of the more technical details. So let's suppose that this is my bi-Lipschitz image, and let's suppose that I have a point z in the image, and for simplicity, I'm going to assume that this point is 0. And I'm also going to assume that 0 is equal to f of 0, and I'm also going to assume that this is a point of differentiability, so f is differentiable at 0. So recall that almost every point in the domain is a point of differentiability. So I'm going to assume that I'm at one of these points, and without that z is an image of one of these points, and without loss of generality, by translating, I can assume that z is actually just equal to 0, and that f of 0 is equal to 0. So this will just simplify some of the details here. Okay, so because f is differentiable at 0, this tells me that it is approximately equal to its derivative here. So in particular, for points near the origin, the image of f accumulates around the plane that is the image of Rm under my derivative. Okay, so in particular, if I blow up this picture here, so this blue ball, and I blow it down to here, what does my picture look like? So the image of my function f is accumulating around this point. So this is still 0, but now this is the unit ball, and this is still my plane, df of x of Rm. Now notice that as this ball gets smaller and smaller, what happens is that my Lipschitz function starts looking more and more like the derivative map. So df of x, y minus x, which means that on small scales, nu, which is my push forward of Hausdorff measure, is going to be asymptotically approximately like df of x push forward Hausdorff measure restricted to Rm. Now, when I take the push forward of Hausdorff measure restricted to a plane, push forward onto the image of a linear transformation, which is another plane, I get just a multiple of Hausdorff measure restricted to the image of this plane. Right, so this is a bit easier to see if df was a linear transformation from Rm to itself, because then you could show this by a change of variables, and this constant here would be the determinant. However, a very similar proof shows the same thing if df maps from Rm into an m-dimensional plane in some higher dimensional Euclidean space. Okay, so if on small scales nu is approximately Hausdorff measure restricted to this plane, what that tells me then is that if I take blowups of nu at 0, if I start zooming in, that means that these blowups here are going to converge weakly to this multiple of Hausdorff measure restricted to Vz, where now Vz is just the tangent plane, so the image of Rm under the derivative map. So this is the picture to keep in mind before I go into the details on the next slide. Okay, so let's first do some setup. So recall that for almost every x in the domain of f, the derivative of f exists and has full rank. So this follows by Sard's theorem. And in fact, when we're working with a bi-Lipschitz map, we don't even need Sard's theorem, but we'll just use it anyway. And we'll let z be the image of any one of these points. So if we can show it for any such z, then we'll be done. Now let phi be some continuous function on Rm with compact support, and pick some radius r such that its support is contained inside the ball center at 0 of radius r. Okay, so now my goal is to show that for any such function phi, that if I take the limit of r to the minus m, tzr push forward nu, that this converges to the integral of phi d some multiple of Hausdorff measure restricted to some m-dimensional plane Vz. Okay, so maybe I'll take that, whoops. I'll take this for now and move it down into this corner, since that's my objective. Okay, so first, one thing that I need to do is keep track of the support of phi. So recall that phi is supported inside the ball center at 0 of radius r. So this integral is the same as just integrating over this ball. Now, what I'm first going to do is factor out this r to the minus m. So this ends up becoming integral of phi d tzr push forward nu. And recall that tzr of w, this is the function w minus z over r. Now, when I integrate a function phi against a push forward of a measure by some function, in this case it's tzr, that's the same thing as integrating phi composed with this function t against this measure nu. Okay, so that means that I can rewrite this integral here as, this is the integral of phi composed with this function, so that's w minus z over r, against the measure nu, w. Now, what happens to my domain of integration now? Well, the new domain of integration is the inverse of this, is the image of this ball under the inverse of this function. So if I take the inverse of tzr, that's the same thing as scaling by r and then translating by z. So the new support of my integral is dz r, big R. Okay. Then recall that nu is the measure f push forward Hausdorff measure restricted to Rm. Okay, so I do the same thing again. I'm going to compose f with this function phi of w minus z over r and then integrate that with respect to Hausdorff measure. So the substitutions I do, I'm going to replace w with f of y. And then notice that, recall that z is equal to f of x. So I'm going to replace z with f of x as well. So this is going to become, let me just make a little bit more room, phi of f minus y minus f of x over r. And then now I'm just integrating with respect to Hausdorff measure against y. And let me move that in a little bit closer. Okay, then also I have to, again, keep track of my domain. So now I have to take f inverse of this ball, and that's my new domain of integration. I'm going to replace this with a slightly larger ball. And I can do that because, again, phi is supported inside this ball. So if I increase the domain of integration, that doesn't change the integral. So notice that because z is inside this ball, then f inverse of z, which is f of x, is also going to be inside this ball. So I'm going to have x is inside here. And notice that for any point inside this ball, its distance from z is at most r times big R, which means that when I take the inverse image of that point, its distance from the inverse image of z, or in other words, the distance from x, is going to be at most L times r big R. And that's because f is a bi-Lipschitz function. So this is contained inside the ball centered at x of radius L r big R. So I'm just going to replace this ball here with, let me draw that a little better. Ball center at x of radius L r big R. Now recall that x was a point of differentiability. So that means that if I take the limit as r goes to 0 of the supremum over y inside the ball center x of radius r of f of x, or sorry, f of y minus f of x minus df of x y minus x over r, this is equal to 0. So notice here that I almost have I have this quantity f of y minus f of x over r here. And I have that quantity essentially right here. So f of y minus f of x over r. So let me kind of rewrite this fraction a little differently. So I'm going to write this as, this is the same thing as taking f of y minus f of x over r, and then minus this over r, and this goes to 0. Okay, and also, if the limit of the supremum of y inside this ball is going to 0, I can slightly enlarge this ball as well to bx LR big R, and this limit will still go to 0. So what this tells me is that as R goes to 0, the function inside phi here is going to be essentially the same thing as this function as R goes to 0. So, or in the limit at least. So what I'm going to do is I'm going to put sort of limit as R goes to 0 here, and let me move this over. Okay, so limit as R goes to 0. So in the limit, I can replace what's inside here with just df of x times y minus x over r. Okay, so now I'm not worried about keeping track of the domain of integration anymore, so I'm just going to get rid of that, and I've used this fact now, so I don't need to keep track of that. Okay, so inside here I have, let me write this a little bit more clearly. So this is df of x times y minus x over r. D Hausdorff measure. Okay, so notice here now that this y minus x over r, okay, well that's, this function right here, txr of y is y minus x over r. So that means that this integral is the same thing as if I was just integrating phi composed with df against the push forward of Hausdorff measure with respect to this function. Okay, so let me just rewrite this here. So this is the same thing as the integral of phi composed with df of x of, let's say, w now, d push forward by zr of Hausdorff measure, and now I'm integrating with respect to this new variable w. Okay, and notice that when I push forward Hausdorff measure with the function txr, okay, I'm just going to get another copy of Hausdorff measure. And in fact, I'm just going to get a multiple of Hausdorff measure. And the multiple that I get is going to be, so this measure here is equal to r to the m times Hausdorff measure restricted to rm. So you can sort of verify that on your own. But notice that when I do that, this rm and this r to the minus m cancel each other out. So what I'm left with in the end, I can just get rid of that txr there. So let me just get rid of all those things. Let me get rid of that, and then I get rid of that. And so I'm left with this integral. And now I'm going to do a similar thing as before. I have phi composed with the function df of x, which is a linear transformation. So this is the same thing as integrating phi against the push forward of this measure under that affine transformation. So I'm just going to rewrite this as just the integral of phi, and I'll just keep the variable w here. So this is the same thing as integrating against df of x push forward of this measure against the variable w. Okay, so now notice now that I have the push forward of Hausdorff measure restricted to Rm by an affine map. Now imagine that this affine map was actually going from Rm back to itself. Then what would happen is that by a change of variables, I would actually just get a copy of Hausdorff measure back times a constant, where the constant is just a derivative of this affine map. Now, if the affine map, instead of going back into Rm, it went to some m-dimensional subspace of Rn, the same thing happens. I'm still going to get a constant multiple of Hausdorff measures. So I'm just going to replace this here with a constant times Hausdorff measure, now restricted to the image of that affine map. So let me give the image of that affine map a name. I'm going to call it VZ. So this is the image of the derivative, the image of Rm under the derivative of f at x. So now I have VZ. And also there's no R present anywhere in here, so the limit I can just take away. And so this is exactly what I want to show, right? So therefore, I've shown that the limit of phi against these blowups is equal to this integral, and it holds for any continuously compacted supported phi. And the integral here is against Hausdorff measure restricted to this plane. And it's sort of natural that the plane VZ should just be the image of the affine approximation to f at the point x.